Hello students, a warm welcome to all of you in ITLS Academy and also welcome to all in our 3 months online certification course on topic nanobiotechnology. In today's lecture we will discuss about the atomic force microscopy. This atomic force microscopy plays a most important role in a field of nanobiotechnology. Now we start today's lecture. What is atomic force microscopy? Atomic force microscopy is the type of microscopy which is used to imaging the biological specimen. Okay. By the help of this atomic force microscopy, we capture the image at high resolution at high resolution. If we want to see the nanoscale structure, then we easily visualize the nanostructure or nanoscale structure by the help of this atomic force microscopy. Okay. In this atomic force microscopy, basically we use a laser light, laser beam to visualize the image. In this microscopy, basically we use a cantilever tip. In this microscopy, basically we scan the surface of our sample. Okay, it operates by the scanning a sharp probe very close to the sample surface to measure the interaction between the tip and atoms of the surface. Suppose this is a biological specimen and we want to visualize the structure of this biological specimen. Suppose this is a any biological sample and we want to visualize this, then we simply scan the cantilever tip with the surface of this sample and analyze the result. In this microscopy, an image will form due to the interaction between tip cantilever tip and atom on the surface. Okay, what is atomic force microscopy? Atomic force microscopy is a type of microscopy by which we easily visualize the nanoscale structures. Okay, and in atomic force microscopy we capture a high resolution image. Okay, for in this the basic principle of imaging is a scanning process. The cantilever tip of the atomic force microscopy scan the surface of the sample and visualize the image. Atomic force microscopy plays a most important role in a field of nanobiotechnology. Okay, in nanobiotechnology, this atomic force microscopy is used for the imaging, for measuring and manipulation of matter at the nano scale. Basically, in a field of life science, we use this microscopy for the visualization purpose. But in a field of nanobiotechnology, we use this technology for imaging purpose, for measuring and manipulation the matter. And by the help of this atomic force microscopy, we easily visualize or study the new material and its unique properties. Okay, in atomic force microscopy has a significant application in nanobiotechnology. This is used to image, measure, manipulation of biological molecules, cells, tissues at the nano scale. By the help of this microscopy, we easily visualize the manipulation of biological sample at the nano scale. Atomic force microscopy have a ability to operate in various environments, including liquid, which is crucial for the biological sample. Make it particularly valuable in study the structure and property of biological sample in their native states. Okay. By the help of this atomic force microscopy, by the help of AFM, okay, this AFM have a unique property. We easily operate this atomic force microscopy in different environment. In different environment. If we want to study the structural and biological property of biological sample in aqueous environment or in gaseous environment. In both environment, we easily visualize or study the different property of biological sample with the help of this atomic force microscopy. That's why this atomic force microscopy plays a most important role in a field of life science as well in nanobiotechnology. Understand the mode of operation. First is a contact mode. Suppose this is a biological sample and this is a surface of biological sample. Okay, and this is a tip of cultivar. Okay, in this contact mode of operation, this tip of the cultivar is stay this tip continuously make a contact with the surface of sample and provide a image and provide a high resolution image. High resolution image. This tip continuously attached to the surface of the sample and give and provide a high resolution image. Okay, there is a drawback of this mode, and the drawback of this mode is sample damage. Sample damage. Okay, in this contact working mode, often softer biological sample will damage due to the continuously direct contact of the tip to the surface of the sample. That's why the softer sample will damage due to this mode. Next is a tapping mode. Next is a tapping mode. In this tapping mode, the cantilever tip of the atomic force microscopy oscillates and taps the surface of biological sample like this. Okay, suppose this is a surface of biological sample and this is a cantilever tip, and this cantilever tip continuously tap the surface of biological sample like this and help to visualize the high resolution image. In tapping mode, this softer biological samples does not damage. Okay, next is a non-contact mode. Okay, in this mode, there is a no physical contact between the tip of the surface, tip of the cantilever and surface of the sample. Okay, in first mode, the tip of the cultilever always make a contact with the sample surface. But in tapping mode, the tip of the cultilever oscillate on the surface of the sample. But in non-contact mode, there is a no physical contact between the tip of cultilever and surface of the sample. Okay, in this mode, the tip stays just above the surface, sensing the attractive force without physical contact. And for it is ideal for high sensitive sample for imaging, where tip contaminates or sample alteration must be avoided. These are the three working mode of AFM. First is the contact mode, tapping mode, and non-contact mode. Okay, now we understand the working mode of atomic force microscopy. Okay, the working mode and the operation of atomic force microscopy is based on atomic interactions. Atomic interaction between the sharp tip of cantilever and surface sample. Okay, first step is probe and cantilever interactions. Okay, this is a cantilever and this is a tip. This is a tip, sorry. Basically, this is a probe tip. Probe tip. And this is a surface of sample. Okay. This cantilever is flexible. And this cantilever and this probe tip have a capability to measure the image in minute force. If there is a minute force, then this tip and this cantilever can easily perform their activity. Okay, okay, and the size of this tip is 10 to 20 nanometer, and the location of this tip is at the end of cantilever. This is the end of the cantilever, and this is the position of probe tip. Okay, this cantilever is flexible, can respond to even minute force between the tip and the surface samples. Okay, as the tip move across the sample surface, the cantilever detect the force such as van der Waals force, electrostatic force, and magnetic force. Okay, whenever the tip is moved on the surface of the sample, this cantilever have a capability to measure the van der Waals force, attraction and repulsion force, electrostatic force, and magnetic force. Okay, the cantilever bends and reflects based on these interactions. Okay, this is a first step. Next step is laser and photo detector. A laser beam is directed at the back of the cantilever. Okay, this is a laser beam. This is the direction of laser beam. This laser beam is directed on the end of this and back of this cantilever. Okay, okay, where the cantilever deflects due to the force between the tip and the sample. the laser beams reflection angle change. Okay, a photodiode records the signal of the reflection. The extraction position of laser on the photo detector indicate the amount of deflection with which correlate the various variation in the samples. Okay, now understand. Suppose this is a surface of biological cell. Okay, and this is the tip. Okay, here the direction of laser beam. Okay, here this is the beam for this is a detector. Basically this is a photo detector. Okay, this laser beam directed at the back of this cantilever. Okay, whenever this cantilever or this tip scan the surface of this biological sample, here, here and here, the scanning process will perform. Okay, due to the interactions between the okay okay as this surface, this tip of the cantilever scan the surface of the biological sample, then the force the force will change. Okay, due to the scanning due to the scanning of biological surface, the force on a tip cantilever changed or deflect or deflects. Due to this reflection, the reflection angle of the laser beam also changed. As this tip scan the surface, then the cantilever force will deflect. Due to the deflection of the force in cantilever, the reflection angle of the laser beam will change, and this changes is recorded by the photo detector, and this changes is recorded by the photo detector. Okay, the exact position of the laser on photo detector indicate the amount of deflection which correlate to various to okay okay these changes are recorded by this photo detector. Okay, and the signal is recorded by this photo detector, and we found our high resolution image. This is a here the photodiode is present. This is a photo. Okay, here this is the surface of biological sample. This is a cantilever. This is the tip of the cantilever. Whenever this tip is moved on the surface, scan the surface of the sample, then the force of the cantilever will change. Due to the changes in force, the reflection angle of the laser beam will change, and this reflection angle or these changes are recorded by the photo detector, and then we find and finally we and then these signal are recorded by the photodiode, and this photodiode then give us and this photodiode provide a high resolution image of biological sample. Next is a feedback loop and precision high control. Okay, in AFM we use a feedback loop. We use this feedback loop to adjust the height of the cantilever in real time. This loop is helped to maintain the constant force and distance between a tip and the surface for accurate imaging. This feedback loop signal the feedback loop signals the scanner to adjust the x-axis or vertical movement. This loop is used for scanning the for adjust the scanning of z axis. Okay, to keep the reflection within a specific range. Okay, this movement data is used to constant a high resolution topographical map of the surface. Okay, in AFM we use a feedback. Why will we use this feedback loop system? Because we want to maintain force and distance between the surface and tip of the cantilever. Why we will maintain the force and distance between the surface and cantilever? Because we want high resolution image. Okay, this feedback loop is also used to scan or adjust the x-axis movement. Whenever we want to study the topographical map of the surface, then we require the scanning in vertical direction also. Okay, for maintaining and for the adjusting the movement of cantilever in x-axis, this feedback loop plays a most important role. Okay, the first work of this feedback loop to adjust the force and distance between the surface and the tip of the cantilever. Second, this feedback loop is very useful for the z-axis scanning. Whenever we want to study the topographical map of the sample, then we require this z-axis or vertical movement of the cantilever tip, and this movement is also maintained by the feedback loop system. Okay, next is a scanner, and now we understand the scanner and stage. In AFM, basically we use piezoelectric scanner, and this piezoelectric scanner can move in axis in x and y axis as well as z axis. This scanner can move in both three directions: x axis, y axis as well as z axis. And this scanner is held to trace the surface to trace the surface of biological sample at the nano scale. This is the working of AFM. Now we understand the working of AFM with the help of this diagram. Okay. This is the surface of biological sample. This is a cantilever. This is very flexible. In here, a scanner is attached on this cantilever, and this scanner is a piezoelectric scanner. This is a tip of the probe, and this cantilever is very flexible. It can easily move in both three directions: x direction, y direction, as well as z directions. Okay, and this is the direction of laser beam, and this is the deflection angle. Okay, whenever this tip is scan the surface of this biological sample, then the force of this cantilever will change. Force is changed. Due to the changes of this force, the deflection angle of the laser beam is also changed, and this changes is detected by this photo diode or photo detector, and by the help of this signaling, this photo detector provide a high resolution image. Okay, this is the basic working of AFM. Okay, if we want to perform this scanning process in air or gaseous environment, then we easily perform this process. If we want to perform if we want to perform this process in liquid environment or aqueous environment, we easily perform this process in both these environment. Okay, now we discuss the advantages of atomic force microscopy in nanobiotechnology. First is the high resolution image. AFM provide a high resolution image at nanoscale. Next is the versatility and environment. Unlike the many electron microscopy, AFM can operate in both air as well as vacuum as well as liquid environment. Okay, and allow for the study of biological and chemical sample in their native state. That's why this AFM plays a most important role in a field of nanobiotechnology. Now we study the advantages of AFM in nanobiotechnology. First is the high spatial resolution. AFM provide a high resolution image at a nanoscale. Next is a versatility in environment. We easily perform this if we want to operate the AFM in aqueous environment, in air environment, in vacuum environment. We easily operate the AFM in air, vacuum, and liquid, and allow the study of biological and chemical samples in native states. Third, 3D surface imaging. AFM generates true 3D dimensional topographical data and this data is essential for the characterization of nanoparticle or nano structure. Okay, there are a lots of advantages of AFM in nanobiotechnology. First is the high spatial resolution. By the help of this AFM or atomic force microscopy, we find a high resolution image at a nano scale. Next is versatility in environment. This AFM can operate in both in this AFM can operate in air, vacuum, liquid environment very easily. Third is a next is a 3D surface imaging. By the help of this technique, we easily generate the 3D topographical data of our sample, and this 3D topographical data is very helpful for the characterization of nanoparticle or nano structures. Now we study the application of AFM in nanobiotechnology. First is a surface topography and morphology. Okay, AFM is widely used to characterization the surface roughness, gain size and structural morphology at a nano scale. For example, it can measure the nanoscale surface feature of thin film, nanowire, nanoparticle, which is a critical in developing electronics and photonic devices. Okay, this AFM is widely used for the characterization of the sample. Next is the mechanical property measurement. AFM can measure the nanoscale mechanical properties like hardness, elasticity, adhesive force, and help the researcher design the material with customized property. It valuable in field like nanoelectronics, biomaterial, which precise mechanical properties are essential. Okay, by the help of this atomic force microscopy, we easily measure the mechanical properties at nanoscale. Next is a biological and medical application. AFM is widely used to examine the biological materials such as protein, DNA, and cells at the high resolution in their native environment. This has had to insight this this has led to insights in biophysics, cellular machine, and drug interaction at nano. Next is a nano manipulation and nanolithography. In nanolithography, AFM plays a most important role. A lithography technique that is a dip pin lithography. In dip pin lithography, the cantilever tip of the AFM plays a most important role, and this tip is also used for for constructing the nano patterns. Okay, beyond the imaging, AFM tip can manipulate the atom and molecules, make it tool for constructing the nanoscale structure and devices. Next is the electrical and magnetic property mapping. Special AFM modes such as the conductive conductive AFM and magnetic AFM allow the mapping of electrical and magnetic property at nano scale. These are the essential for study development of nano devices such as high density data storage and nanoscale transistors. These are the application of AFM. Limitation and challenges. Okay. First is a limited scan speed. Scanning large area at high resolution take time. Okay, which can be drawback for certain applications. Next, sample preparation. AFM is sensitive to rough or uneven surface, which may require careful sample preparation. Next is a force sensitivity. High force between the tip and the sample can distort or damage the biological sample. Okay, these are the limitations and challenges of AFM. This is all about today's lecture. In this video lecture, we discuss about what is the AFM, what is the working of AFM, what is the application of AFM in nanobiotechnology, limitation and challenges. Okay. Please follow ITLS Academy on Instagram, Facebook, Twitter, YouTube, and also get it on Google Play Store. Thank you so much for watching my video. Please like, share, and subscribe ITLS Academy. Thank you.